Hi, welcome to 6.1 BC Notes today. We're going to be talking about Euler's method and Euler's method for maybe finding a particular solution to a differential equation and reviewing a little bit on slope fields. So you should have your notes in front of you. And first of all, Euler's method, it's just a numerical approach to approximate the particular solution of a differential equation. And we'll kind of review as well on the back side how to do slope fields as well as solving for a particular solution. Oh no, I don't have a particular solution on the back, but just solving for a generic solution for a differential equation. Now first of all, I want to think about our formulas here that you see on the front page. If I'm looking at these formulas, let's see if I can explain these here. I have x sub n is equal to x sub n minus 1 plus h. Now I want to think of h as my delta x. That's the increments of h coming up from, I don't know, from our starting point. Say we're going to have increments of zero point 0.1 and we can estimate like a value of our function at a particular x value as we increase it by little, 0.1, 0.01, the smaller, of course, the more accurate we're going to be. So if you look at this, that's just x sub the previous x value plus our delta x or plus our increment. If I have my y sub n, what I have is my y sub n minus 1. Again, this is a recursive formula because I'm just referring to the previous term, plus I have h, which is my delta x, times my y prime of, whoops, don't want to write it like that, my derivative of my previous term. Now if I think about this, this is reminding me of my slope formula, y equal mx plus b, where m is my slope, right there. I think about this, if I want to rearrange this formula, I have y sub n minus y sub n minus 1. That is equal to my h times my y prime of n minus 1. Now I don't like using h's when I'm trying to really think about this. So basically, and I don't like using this y n minus y sub n minus 1. What this actually is delta y is going to be approximately my h, which is my delta x, and my y prime, isn't that my dy dx? That's the way I like to think about it. So on the side of your, or in that box up there, if you want to put that part of your formula there to find your delta y, I'm just going to take my delta x and multiply it times the derivative of y with respect to x, which is usually given in your problem. So basically this is kind of just a bunch of tables. I guess one other thing I could mention here is I have dy would be approximately delta x. Remember, if you have a very small values of delta x and delta y, this will be very close to my f prime of x times dx. Thinking about that, my derivative, there it is, my f prime of x, my delta x is my dx. So basically what we have here is we have a curve that we are trying to estimate using Euler's method of, you know, it may not be right on the curve, but I'm kind of going from here, and maybe I don't start there at the origin either, maybe that's kind of deceiving. Then I'm going to come very close to the curve, but maybe not quite there. But oh, that's a terrible drawing. Let me start again. Here's my curve. This is my actual curve, and here's one that we're going to try and get to. So say the point's right there. We're not going to be right on the curve. Here's my delta x, and here's my delta y. And we're basically finding that segment, and that is just a linear, y equal mx plus b, which is reminds me of this one right here. Okay, and then I'll go to the next one. Say the next one's right here. It's another segment. So we'll be estimating. We're just going to be very close to approximating where this, say, y value is here versus the x value would coordinate to it down here, just to kind of see how close we can get. Again, solving differentials using Euler's method. So here we go. I'm going to do this maybe a little bit different than what the book explains, just because I would prefer to use my delta y is equal dy dx times delta x. So here goes example 1. I'm supposed to use Euler's method with h equal to zero point 0.2 to estimate y sub 1. That's what I'm going to try and find eventually. I know y prime is equal to y minus 2, and my initial point, y of 0, is equal to 4. So now this h right here I'm going to say is equal to delta x, since I like using delta x instead of h, but I know that's what's in the book. So I'm going to start with basically a huge table, and make sure you have your calculators. You're going to probably be needing them. It goes faster at least. This is x and this is y. And they'll tell you like n is equal to 10. If n is equal to 10, if you like to put that chart in, I start with your 0 is your initial value, which is 0 and 4. And then 1 would be their next value, 2 would be the next value, and so on. So if you have a problem where they say where n is equal to 10, that's how you would work that problem. Now if I look here, my delta x is 0.2, and I want to find y of 1. So basically I'm going to go through my chart here and add 0.2 each time. So I have 0, then I'll have 0.2, and then I'll have 0.4, and then I'll have 0.6, 0.8, and then 1. So I just add my delta x or my h every time to my x value. Now my y's, this is where we have to work on this. Now you have a choice. You can, if you want to read the textbook, or I can even show you when I get back, and use this method, you can. They're very similar, but I like saying, okay, I'm going to find my delta y, and the way I'm going to do that is I'm going to find my dy dx, which is my y prime, times my delta x. Oh, I don't want it to look like that. That looks really bad. I want to find my y prime of x times my delta x. Okay? So if I look at this, I'm just even going to just go ahead and mark that out and just say, okay, what is my y prime? Well, that is y minus 2 from this right here. And what is my delta x? That's my 0.2. So let's take and let's see what is y in this particular example. And let's see if I can get that arrow to show up. See this right here? Oh, that's not what I wanted. I'm looking at that 4 right there. That's the y value that I'm going to plug in. 4 minus 2 times 0.2. Well, what is 4 minus 2? Well, we all know that's 2 times 0.2. I'm going to get 0.4. So I take and add that to the 4 that I have there already. So what is 4 plus 0.4? Well, that's going to go right here, 4.4. So hopefully you followed that. Now I'm going to pick up where I left off again. You just do it again. Take 4.4 minus 2 times 0.2. So I get 2.4 times 0.2. I get 0.48. What do I add that to? I add it to the 4.4. Okay. So I'm going to get 4.88. And then you just keep doing this. So here I'm going to get 4.88 minus 2 times 0.2. I'm going to get 0.576. What am I going to add that to? 4.88 plus 0.576. So I get 5.456 right there. See how this can get a little tedious? 5.456. So if you ever hear people talk about finding your differential using tables, this is what they're doing. They're actually using Euler's method. So I'm going to, and a lot of times I will not write down 5.456 minus 2. I'll just go ahead and write 3.456 times 0.2. I did that on my calculator and I got 0.6912. And I add that, so you know where I'm getting that. I add 5.456 to 0.6912, and I got 6.147. So then I go back and I'm like, okay, subtract 2 from 6.147 because that is my y value. And so I get 4.147. Oh, that looks really bad. 4.147 times 0.2, and I get 0.82944. Add that to 6.147, and I get 6.977. So I'm finally done. So I have y of 1 is approximately 6.977. And that's using Euler's method to estimate y of 1. Now, if you have any questions, I'm sure there are people in the classroom that can help you. You can put this on pause before we do the next problem. Actually, why don't you put the video on pause and everybody work that with a study buddy, and you can turn it on here in a minute and compare work. So I'll go ahead and put this on so you can check that. So go ahead and do that. Okay, so on this particular one, if I'm looking at my y prime, this is real important that you get this out of your problem. Y prime is your y minus 1. That is what goes right here in your formula. Your h, which is your delta x, is your 0.1, and you get that at your problem from your problem as well. We need to find y of 0.5, so if I start at the 0.03, then I would just be increments of 0.1, so I have 0.1, 0.2, 0.3, 0.4, 0.5. So assuming that you've already got this done, you just need to check real quick. I'm taking 3 minus 1 to get a 2 times 0.1. I got 0.2. Add that to 3, I got a 3.2. Then I take a 2.2, because I took 3.2 minus 1, times 0.1, I got 0.22. Add that to the existing y, so I get 3.42. Then I take 2.42 times 0.1, and I got 0.242. Boy, I hope I didn't make any mistakes here. I'm sure if I did, you'll find them. And then I add that to the existing y value, so that would be 3.662. So I have 2.662 times 0.1 to get 0.2662. Add that to the existing y value, so I got 3.9282. Subtract 1 from that, so I get 2.9282 times 0.1 to get 0.29282. Add that to the existing y value, and I get 4.22102. So that one I stop there, and that was again, oh shoot, what was that? 4.22102. So I can say that y of 0.5 is approximately 4.221, and we can just round that to the nearest 3 places past the decimal, since that's what we always need for the AP exam. Just to summarize, when you're using Euler's method, it's very important that you have to have a starting point, and you have to have an initial slope formula or a y prime, and you have to know your increments. So a lot has to be given in order to be able to use Euler's method. Okay, now on the back side of these notes, I'm only going to go through the second problem in the back. You guys can probably work together to finish example 1 and example 2, but let's kind of review slope fields. And we've done this before, so this is nothing new. Here's example 2. I have dy dx equal to y, and I need to sketch that slope field. Now, you see a pretty big graph here, 5 by 5, and that's a lot. On an exam, you will probably not be given anything that large. So let's just kind of do maybe a 3 by 3. If we just want to do that much of the graph, that would be fine with me. Sometimes you're given a little, maybe you need to do more of the quadrants 1 and 2 to get your actual equation. But remember how we find our little slope fields is let's do it like this, where I have my ordered pair xy and then my dy dx over here. Say I want to plug in the point 1, 0, and I'm plugging it into my derivative formula that's given. Well, it's just my y value in this case, because dy dx is equal to y. So at the point 1, 0, I have a slope of 0. So I put a horizontal little dash there. If I want to plug in, say 1, 1, I plug that into my derivative and I just get y to be 1. So right here at the point 1, 1, I need to put a slope of 1. There it is. Say I want to plug in the point 2, 2, so my y value is 2. Now you just have to make sure you have a bigger, steeper slope than what you had before. Okay, and sometimes we can use rulers to kind of help us out on that. Say I want to plug in something like -1, -1. I just get a y value of -1. So I go to the point -1, -1, my y value is -1. So say I want to put in -2, -2, my y value is -2. Okay, so you get the idea, so you can go ahead and fill in maybe the rest of that. If I look at this, actually, I know that if anything along here will have a 0 slope. Once I figure these out, my y value is, say I have 2, 1, my slope is 1. So these are all going to have a slope of 1. Right here, these are all going to have a slope of 2. So once you kind of get the pattern, you can kind of look at that. These will all have a slope of -1. These all have a slope of -2. A little bit steeper than before. These will all have a slope of 3, so again, steeper than what you had before. That's what we're kind of looking for. And this is a slope of -3. So there's just drawing the slope field. And now why don't we just kind of practice on this one as well, finding the general formula for this differential if I were to solve for that. I have dy dx equal to y. Now remember, you need to separate the variables, which means you put your y's on one side, your x's on the other. And then the next step would be to do the integral of both sides. And then the integral of 1 over y, we all remember that to be the natural log of y, equal to the, the integral of dx is just x, and you got to put a plus c either on the left side or the right side, and I always prefer the right side. Now we do have to solve for y here, so let's put this in exponential form. E to the x plus c is equal to y. Are you remembering this from first semester? This is probably just a really good review. So then remember, from here we didn't leave it like this. We would rewrite this as e to the x times e to the c. And e to the c, remember this right here is just a constant. So I have my constant times e to the x equal to y. So there is a general solution. If we were given a point, we can then plug it in for x and y and solve and get a particular solution, but we did not have those. Okay, so there you go. You've got 1 and 2 that you can practice doing your slope fields on. Today you've got homework from the book as well as a worksheet to work on. So there you go. You are ready to get busy on that. Thanks a lot and have a good day.